Hello students, welcome to my channel. Today I will continue the chapter Haloalkanes and Haloarenes, and this is my third lecture. Today I will discuss the topic aromaticity and the methods of preparation of haloalkanes and haloarenes. So before we go aromaticity, you should know what is aromaticity. Now aromaticity is a very important property in organic chemistry. In organic chemistry, aromaticity is a property of cyclic structures with a ring of resonance bonds that gives increased stability compared to other geometric structures. Initially, the compounds which possess the properties of aromaticity are called aromatic due to their fragrance, but later on it is found that aromaticity is referred to the increased stability of the cyclic organic compounds. So aromaticity play a vital role in organic chemistry. প্ৰথমতে যিবোৰ যৌগই aromatic ধৰ্মসমূহ লৈছিল সিহঁতক aromatic বুলি এই কাৰণে কোৱা হৈছিল কাৰণ সেইবোৰ সুগন্ধি যুক্ত আছিল, কিন্তু পিছলৈ দেখা গৈছিল যে aromaticity ধৰ্মটো যৌগবোৰৰ সুস্থিৰতাৰ লগত জড়িত. Now we will have characteristics for aromaticity. First, the molecule should be cyclic, the molecule should be planar, the molecule should have alternate single and double bonds so that the molecule can undergo resonance. The most important property is that the molecule should obey the Haeckel rule. In 1930, Erich Haeckel proposed a theory to determine the aromatic compounds. According to this theory, the molecule should have 4n plus 2 pi electrons, where n cannot be fraction, it must be 1, 2, 3, 4 like this. But this theory is applicable only when the molecule follows the characteristics 1, 2 and 3. So this Haeckel theory is discussed at the last. Now you can ask me, students, that from where these pi electrons will come. These pi electrons will come from pi bond and the lone pair. Along with aromaticity, you should also know what is an anti-aromatic compound. Anti-aromatic compounds are also those compounds which obey the cyclic, planar, alternate single bond and double bond, but according to Haeckel rule, anti-aromatic compounds should possess 4 and pi electrons, where n is equal to 1, 2, 3, 4, etc. So we will see the application of these properties in case of aromatic, non-aromatic and anti-aromatic compound. First of all, we have taken a very simple compound which is familiar to all of you. This is called benzene, and we will see all the properties of aromaticity for this compound one by one. First of all, it is cyclic. You can see the compound. Next, it is a planar molecule because all the carbon atom is sp2 hybridized. Next, the molecule will undergo resonance because the molecule has alternate single bond and double bond. So since this molecule obey all the three characteristics of aromaticity, so we can proceed for the Haeckel theory. This molecule has 6 pi electrons. You see, this is 1, 2, 3 pi bonds. That means 6 pi electrons. So 6 equal to 4n plus 2, that is n equal to 1. So it also obey Haeckel rule. So the molecule is aromatic. It's a very simple. You can also determine the molecule is aromatic or non-aromatic or anti-aromatic in this way. Next we will go to the non-aromatic compound. Here I have taken a very simple compound, cyclopropene. Again we will see all the characteristics of aromaticity one by one. First of all, it is a cyclic one. You can see the molecule, Next, it is a planar molecule. Now what about the resonance? You see here only one pi bond is there, that means 2 pi electron. But to undergo conjugation there is no any other pi bond, and this carbon atom is not in conjugation with any other atom in the molecule. So the molecule will not show the resonance. So it is meaningless to see the Haeckel theory for this molecule. So we can say that the molecule is non-aromatic. Again we will take another heterocyclic compound with nitrogen atom and the lone pair on nitrogen atom. There is one lone pair on the nitrogen atom. For this compound again we will see all the properties of the aromaticity one by one. So it's a cyclic compound. It is a closed structure, so cyclic. It is a planar molecule, and it will undergo resonance because you see there is 2 double bond and alternate single bond double bond is present. So it will undergo resonance. It is 1 pi bond, 2 pi bond, that means 4 pi electrons, and in alternate position. There is one lone pair on the nitrogen atom, but this lone pair will not take part in resonance since this lone pair is not in conjugation with any other atom. So we will neglect this lone pair. So since it obeys all the 3 characteristics of aromaticity, we can go for the Haeckel rule. So it has 2 pi bonds, that means 4 pi electron, that is equal to 4n. So it is not aromatic, but n equal to 2, so it is anti-aromatic. So in this way you can determine whether the cyclic molecules are aromatic, non-aromatic or anti-aromatic. We will take some more examples. Here we will take all the examples which obey all the 3 characteristics, first 3 characteristics of the aromaticity. So this is furan. It is a heterocyclic compound with oxygen atom having 2 lone pair of electrons on it. So it is cyclic, planar, and it will undergo resonance as the alternate single bond double bond is present. Now the number of pi electron is 6. 2 pi bonds, that means 4 electrons, pi electrons, and 1 lone pair is used in resonance, so 6 pi electrons. So that is why n equal to 1 according to Haeckel theory. So the molecule is aromatic. Though the 2 lone pairs are present in furan, 1 lone pair will be not used. The second example is anthracene. It is cyclic, planar, and alternate single bond double bond is present, and number of pi electron is 14, and according to Haeckel theory n equal to 3 using 4n plus 2 equal to 14, so the molecule is aromatic. Next we have taken 1,3-cyclobutadiene. Here the molecule is cyclic, planar, alternate single bond double bond is present, and number of pi electron is 4, that is equal to 4n. So n equal to how much? It is equal to 1. So the molecule is not aromatic, but it is anti-aromatic. Again we have taken another example, 1,3,5,7-cyclooctatetraene. It is cyclic, planar, and alternate single bond double bond is present, and how many pi electrons? 8 pi electrons, which is equal to 4n, and therefore n equal to how much? 2. So it is not aromatic but anti-aromatic. So in this way you take some more other examples and try to determine whether the molecules are aromatic, non-aromatic and anti-aromatic. Next we will go to a different topic, preparation of alkyl halides and haloarenes. In your syllabus, preparation is given from alcohol, hydrocarbon, Sandmeyer reaction and halogen exchange reaction. But here I will discuss preparation of alkyl halides and haloarenes only. from alcohol. So here alcohol reacts with hydrogen halide in presence of zinc chloride to produce alkyl halide and water. Here halogen replaces hydroxide ion and produces alkyl halide, and hydroxide ion takes hydrogen ion from hydrogen halide to form water. This happens in presence of Lucas reagent. This process is called Group's process. In the next process, alcohol reacts with sodium bromide and sulfuric acid to produce alkyl bromide, sodium bisulfate and water. Here again bromide replaces hydroxide ion and alkyl bromide is formed, and sodium reacts with sulfate to form sodium bisulfate and water. In the next process, alcohol reacts with phosphorus trichloride to produce alkyl halide and phosphorus acid. The reaction is not balanced, so we put 3 in before alcohol and the reaction is balanced. Here halide ion replaces hydroxide, we will get the alkyl halide, and due to the presence of phosphorus we will get the phosphorus acid. So this reaction is restricted only to chlorine and bromine. That means only alkyl chloride and alkyl bromide can be prepared by this reaction. In the next process, alcohol reacts with phosphorus pentachloride to produce alkyl chloride, phosphoryl chloride and HCl. Here chloride replaces hydroxide ion and we get the alkyl chloride, phosphoryl chloride and hydrochloric acid. In the next process, alcohol reacts with halogen in presence of red phosphorus to produce alkyl halide. Here the phosphorus reacts with halogen to produce phosphorus trichloride, and that will react with the alcohol to form alkyl halide. Here halogen replaces hydroxide ion to produce alkyl halide, but it is a combination of 2 processes as I have said. This reaction is restricted to bromine and iodine only. In the next process, alcohol reacts with thionyl chloride to produce alkyl chloride, sulfur dioxide and hydrochloric acid in presence of pyridine. Now here chloride replaces hydroxide ion to produce alkyl chloride, and due to the presence of sulfur we get the sulfur dioxide and hydrochloric acid. The important thing about this reaction is that sulfur dioxide is gaseous and hydrochloric acid is gaseous instead, so they will go out and we will get only the required product, alkyl chloride. This process is known as the Darjen process. This process is the best process among these processes to produce alkyl chloride from alcohol, as the byproducts go out and we get the alkyl chloride without the separation from byproducts. So this is the best process, and in other process you have seen the byproducts are formed when we need to separate the alkyl halide from the byproducts. Thank you students, hope you will enjoy this video, and in the next lecture I will continue this chapter. Till then, bye bye.